Welcome back. In Lesson 1, we built mathematical models as weighted combinations of features. Now I'm going to guide you through the next question. Once we have chosen a model family, how can observations determine its unknown parameters? We will begin with exact simultaneous equations, then discover why merely counting equations is not enough. We need independent information, captured by the rank of the design matrix. That leads to identifiability, whether different parameter effects can actually be separated. Finally, we will introduce noisy observations and see why an exact solution may not exist at all. At that point, approximation is no longer optional. It becomes the mathematical problem. We will stop just before choosing a particular approximation rule. Least squares belongs to the next lesson. Our purpose here is to understand precisely why it is needed. Let us reconnect the notation. The prediction model y hat equals w0 plus w1 times x is the familiar line y equals mx plus c, with w0 corresponding to c and w1 corresponding to m. We use weights because the notation extends naturally to many parameters and basis functions. The hat is essential. A value y without a hat was observed in a dataset. A value y hat was calculated by the model. Even if the two numbers happen to agree, they came from different sources. Keep that distinction in mind because the entire lesson asks whether one shared parameter vector can make the model predictions agree with all the observed outputs. Begin with the easy direction. Suppose the parameters are already known. w0 equals 1 and w1 equals 2. The model is y hat equals 1 plus 2x. At x equals 0, the prediction is 1. At x equals 1, it is 3. At x equals 2, it is 5. And at x equals 3, it is 7. Each input travels through the same rule. When the parameter values are known, prediction is routine. Insert the input, evaluate the weighted terms, and obtain the output. Modeling reverses this direction. The inputs and observed outputs are supplied, while weights are unknown. Suppose we observe the point 1, 3 and choose a straight line model. Requiring an exact match gives 3 equals w0 plus w1. This is one scalar equation involving two unknown parameters. Can it determine a unique line? No. The pairs 1 and 2, 2 and 1, 0 and 3, and -7 and 10 all satisfy the equation. In parameter space, the allowed pairs form a complete line. In the original graph, every one of those parameter pairs selects a different straight line passing through the same observed point. So our first principle is simple. One observation generally cannot determine two unknown parameters. Add the observation to 5. It gives 5 equals w0 plus 2w1. Subtract the first equation from the second. The intercept cancels, leaving w1 equals 2. Substitute back to obtain w0 equals 1. But two constraint lines intersect at one point in parameter space, and that point selects the line y hat equals 1 plus 2x. This is school algebra viewed as parameter determination. But do not conclude that any two written equations determine two unknowns. The observations succeeded because they supplied genuinely different and mutually compatible information. Now, repeat the same observation. 1, 3. Both rows produce exactly the same equation. 3 equals w0 plus w1. We may write it twice, 5 times, or 1,000,000 times, but its information has not changed. Geometrically, the second constraint lies directly on top of the first. We still have infinitely many possible parameter pairs. The number of rows is therefore not the same as the number of independent constraints. This is the first place where rank will eventually replace simple counting. Consider instead the observations 1, 3 and 1, 5. Now, the first requires w0 plus w1 to equal 3. The second requires the identical expression to equal 5. No parameter pair can satisfy both. The constraint lines in parameter space are parallel rather than coincident. This separates two questions. Consistency asks whether any solution exists. Uniqueness asks whether an existing solution is the only one. A system can have one solution, infinitely many solutions, or no solution. For two parameters, two independent and consistent equations can determine the parameters uniquely. The same reasoning extends beyond one input. A house price model may use floor area, x1, and age, x2. Let me write the model on the board. Y hat equals W0 plus W1 times x1 plus W2 times x2. With weights 50, 2, and negative 1.5, a 100 square meter, 10-year-old house receives contributions of 50 plus 200 minus 15. The prediction is 235 in the chosen unit. Once weights are known, the forward calculation is easy. In reverse, however, we must determine three parameters. That requires at least three independent scalar constraints. Suppose the exact relationship is hidden inside three observations. At x1 equals 0 and x2 equals 0, y equals 1. That isolates the intercept, w0 equals 1. Now let us proceed to the next step. Next, set x1 to 1 while x2 remains 0, and observe y equals 3. The change isolates w1, giving 2. Finally, set x2 to 1 while x1 remains 0, and observe y equals 4. That isolates w2, giving 3. The resulting model is y equals 1 plus 2x1 plus 3x2. These observations were not merely numerous enough. Their variation separated the three-parameter effects. This is a miniature example of experimental design. A model with p unknown weights requires at least p independent scalar constraints for unique identification. Count carefully. W0 and W1 means two parameters. W0 through W2 means 3. A model with 3 raw inputs and an intercept has 4 parameters, not 3. The intercept is an unknown coefficient and must be identified like every other weight. This is only a necessary counting rule. Having p rows does not guarantee p independent constraints. The design matrix must also have rank p. Return now to the general model from lesson 1. Y hat of x equals the sum from j equals 0 to p minus 1 of w sub j times phi sub j of x. For observation I, we evaluate every chosen basis function at x sub I. Those evaluated numbers form one feature row. The weights remain shared across all observations. The ordinary linear model uses the constant and raw inputs as basis functions. A curved model may use x squared, sine, exponential, or localized components. As long as the weights enter through a sum, the equations remain linear in the unknown parameters. Choose the features 1, x, and x squared. Their weighted combination is y hat equals w0 plus w1x plus w2x squared. The graph may curve as x changes, yet every observation still gives a linear equation in w0, w1, and w2. This distinction matters enormously. Nonlinear features do not prevent us from using simultaneous equation and matrix reasoning, provided the unknown parameters themselves appear only for a weighted sum. Let us build an exact quadratic from the points 0, 1, 1, 4, and 2, 9. At 0, the equation immediately gives w0 equals 1. At 1, the remaining weights satisfy w1 plus w2 equals 3. At 2, after substituting the intercept and simplifying, w1 plus 2w2 equals 4. Subtracting gives w2 equals 1, and then w1 equals 2. The recovered model is 1 plus 2x plus x squared. 3 suitably distinct observations determined 3 parameters. Now repeat the point 1, 4, 3 times. Every row says 4 equals w0 plus w1 plus w2. Many triples satisfy that single condition, 1, 2, 1, 4, 0, 0, or 0, 1, 3. The row count is 3, but the independent information count is 1. We need a mathematical object that exposes this structure. That object is the design matrix, and the measure is its rank. For observation I, place the evaluated features side by side, phi 0 of xi, phi 1 of xi, continuing through phi p minus 1 of xi. Multiply this row by the column of weights. The dot product produces y hat sub I. This one row is the complete model calculation for one observation. It records what each parameter would contribute at that input. Stack the feature row for every observation. The result is the design matrix, capital free. It has n rows, one for each observation, and p columns, one for each basis function n parameter. Stack the predictions into y hat bold and the weights into w bold. Then every model calculation is compressed into y hat bold equals phi w bold. Matrix notation has not changed the mathematics. It has packaged n-related scalar equations into one structured system. Why call it a design matrix? Because it records both the observed inputs and the structure we chose. Now, for a line, each row is 1 and x. Let me pause on that idea. Each row corresponds to a single observation, and we are including a column of 1s for the intercept and a column for the input x. For a quadratic, each row is 1x and x squared. Notice what happens here. We add another column to capture the curvature in our model. For a two-input linear model, it is 1, x1, and x2. So rows correspond to observations, and columns correspond to parameter effects or basis functions. The element x sub 32 means the second raw input of the third observation. Let us build this step by step in our minds. Changing the model family changes the columns even when the raw dataset remains the same. If every observation follows the selected model exactly, observed y equals predicted y hat for every row. Now I'm going to guide you through the matrix equation where it becomes y in bold equals phi times w, also in bold. For the 2 points 1, 3, and 2, 5, phi contains the rows 1, 1, and 1, 2. Multiplying by w0, w1 gives the observed vector 3, 5. Let us expand the product, and we recover exactly the two equations solved earlier. Notice what happens here. The matrix is not an abstraction replacing the algebra. It is the algebra organized at scale. Now we can name the missing idea. Rank measures the number of independent directions or patterns represented by a matrix. For modeling, the most useful interpretation is this. Rank tells us how many independent parameter effects can be distinguished from the observed data. A design matrix with p columns has one column for every parameter, so its rank cannot exceed p. To distinguish all p effects, we need rank equal to p. This condition is called full column rank. Consider the columns 1, 1, 1 and 0, 1, 2. The first is the prediction pattern produced by changing the intercept. Every row moves equally. The second is the pattern produced by changing the slope. Observations move by amounts proportional to their inputs. Neither column is a constant multiple of the other. They represent two independent patterns, so the rank is 2. That is enough to identify two parameter effects in an exact, consistent system. Now let the columns be 1, 1, 1, and 2, 2, 2. The second is exactly twice the first. Changing its weight produces the same prediction direction as changing the first weight by a different amount. The data cannot tell which parameter caused the shared effect. Although the matrix has two columns, it has rank 1. A two-parameter model cannot be uniquely identified from it. A larger matrix can hide the same problem. Here, the third column is twice the second. The design matrix has 3 columns but only 2 independent column patterns. Its rank is 2. The contribution assigned to the second weight can be exchanged with the contribution assigned to the third while leaving every prediction unchanged. Counting 3 columns would miss that ambiguity. Rank exposes it immediately. A parameter vector is identifiable when the observations and chosen model determine it uniquely. Suppose W and W tilde produce exactly the same predictions. Subtracting gives phi times their difference equals 0. If phi has full column rank, the only parameter difference producing 0 is the 0 vector itself. Therefore, W equals W tilde. If rank is deficient, a non-zero difference can hide in a null direction and predictions remain unchanged. This is why full column rank gives parameter identifiability in the exact linear in parameters model. Suppose every observation in a two-input model satisfies that x2 equals 2 times x1. Now, substitution reduces the model to w0 plus the combined quantity w1 plus 2w2 multiplied by x1. The data can identify that combination, but cannot decide how to divide it between w1 and w2. 1 million observations obeying the same dependency still leave the effect confounded. We need not only more observations, but more diverse situations in which the inputs vary independently. Here is the geometric picture. Treat each design matrix column as a vector across all observations. If two columns point in different directions, their weighted combinations span a plane, and the rank is 2. If one column is a multiple of the other, both lie on the same line, and the rank is 1. Each column describes how one parameter changes the complete prediction vector. Rank is the dimension of the prediction directions available independently. For the quadratic basis 1x, x squared, the distinct inputs 0, 1, and 2 produce rows 1, 0, 0, 1, 1, 1, and 1, 2, 4. This matrix has rank 3, so 3 exact observations uniquely determine 3 coefficients. If the last input repeats 1, the last 2 rows become identical and rank falls below 3. For a polynomial with p coefficients, p distinct scalar inputs normally create a full rank polynomial design matrix. This is the Van de Waals structure encountered in interpolation, though the name is less important than the independence. Let phi have n rows and p columns. N counts observations, p counts parameters. Comparing them gives 3 regimes. If n is smaller than p, the system is underdetermined. If they are equal, the matrix is square. If n is greater than p, the system is overdetermined. These labels describe dimensions, not whether a solution exists or is unique. Rank and consistency must still be examined. When n is less than p, there are fewer scalar equations than unknown weights. Rank cannot exceed the number of rows, so full column rank is impossible. If the equations are consistent, there are generally infinitely many exact parameter vectors. A 4-parameter model with only 2 observations cannot be uniquely identified from those 2 constraints. Extra assumptions or additional independent observations would be required. When n equals p, phi is square. If it also has full rank, it is invertible, and the unique exact solution can be written w equals phi inverse times y. But square shape alone is not enough. A square rank-deficient matrix has no inverse. Depending on the observation vector, the system may then have infinitely many solutions or no solution. Never replace the condition full rank with the weaker statement square. When n exceeds p, one parameter vector must satisfy more equations than there are unknowns. This is overdetermined. It can still be exactly solvable. 100 perfectly generated points on y equals 1 plus 2x are all satisfied by the same intercept and slope. The extra observations confirm the relationship. Overdetermination does not itself imply inconsistency. Real-world noise is what usually makes the many conditions conflict. Let us settle the classification. Underdetermined means too few rows for full column rank. Square means equal counts, but uniqueness still requires full rank. Overdetermined means many simultaneous conditions. An exact solution remains possible for perfect data. Dimension counts equations and unknowns. Rank counts independent parameter directions. Consistency asks whether the observed vector lies among the predictions the model can produce. Identifiability asks whether one unique parameter vector produced it. In the ideal deterministic case, a true parameter vector W star generates every observed output exactly. Y equals phi W star. The observed vector lies in the set of prediction vectors available from the chosen columns. Two independent points can determine a line, while additional exact points can confirm it. This ideal case is invaluable for understanding structure, but practical observations rarely remain on a simple model with perfect equality. Consider study time and examination score. Students who study for the same duration can receive different scores because of prior knowledge, sleep, stress, health, teaching quality, question difficulty, and random variation. A recorded measurement can also contain error or rounding. The model includes only part of the real process. Therefore, the observed output usually differs from the model prediction. This is not a failure of arithmetic. It is a feature of modeling the real world with limited information. We represent the discrepancy by writing y sub I equals y hat sub I plus epsilon sub I. Epsilon is a part of the observed output, not explained by the model prediction. For the basis function model, y sub I equals the weighted feature sum plus epsilon sub I. Stack the observations, and we obtain y bold equals phi w bold plus epsilon bold. The term noise is broad. It can include measurement error, natural variability, omitted variables, rounding, and environmental or temporal changes. Let us distinguish several mechanisms. Now, a scale can measure imperfectly. Similar patients can respond differently. A house model using only area and age can omit location, condition, transport, view, and demand. Recorded values can be rounded, and conditions can change over time or place. We may collect these effects into epsilon for the present discussion, but they do not all have identical scientific meanings. The common point is that the simple prediction does not determine the observation exactly. Noise is not the only source of disagreement. Suppose the true relationship is y equals x squared, but we insist on a straight line. Even perfectly measured points cannot all lie on one line. That systematic discrepancy is model mismatch. The selected family is too limited to represent the pattern. In practice, an observation minus prediction difference may contain both unexplained variation and mismatch. More data can reveal the curvature more clearly, but no amount of data makes a line equal a genuine quadratic everywhere. Model choice and parameter estimation are separate problems. Now, watch noise create inconsistency. The points are 0, 1.1, 1, 2.9, and 2, 5.2. Fitting the first two exactly gives W0 equals 1.1 and W1 equals 1.8. At x equals 2, that line predicts 4.7, but the observation is 5.2. The first two equations determine parameters that fail the third. No shared straight line passes through all 3 points. Choose the first and third points instead. The intercept remains 1.1, but the slope becomes 2.05. At x equals 1, this line predicts 3.15 rather than the observed 2.9. A line has two parameters, so any 2 points with distinct inputs can select a line. But different pairs select different lines. Why discard the remaining evidence, and why privilege one pair? An estimation method should use all available observations rather than an arbitrary subset. One sensor reading may be too high and another too low. A model based on only 2 readings can depend heavily on accidental errors. With the 5 observations 1.1, 2.9, 5.2, 6.8, and 9.1 across inputs 0 through 4, no line matches every point, yet the overall pattern is visibly close to slope 2 and intercept 1. Many observations provide repeated evidence about the shared structure. They help only when they add variation. Repeated dependent inputs cannot separate confounded effects. Suppose a model contains x1 and x2, but they are equal in every observation. More rows repeat the same combined direction, and cannot separate the two weights. Good data, therefore, require both quantity and diversity. Experimental design asks how to observe or control situations so the relevant inputs vary independently enough to distinguish their effects. Rank is not merely a property checked after data collection, it can guide how informative data should be collected. We now name the disagreement. The residual for observation I is r sub I equals y sub I minus y hat sub I. A zero residual means an exact match. A positive residual means the observation lies above the prediction, so the model underpredicts. A negative residual means the observation lies below the prediction, so the model overpredicts. The sign convention matters. For example, if y is 7 and y hat is 6.5, the residual is positive 0.5. Stack the sign discrepancies into the residual vector r, bold. Since the complete prediction vector is phi w, the residual vector is y minus phi w. This is one of the main equations of Lesson 2. Every possible parameter vector creates one point in prediction space and one corresponding residual vector pointing from that prediction to the observed vector. Different parameters produce different residual patterns. When no exact solution exists, several parameter vectors may appear reasonable. One line may fit early points closely and miss a later point. Another may distribute errors more evenly. A third may avoid one unusually large error. Which is best? Mathematics cannot answer until we define a comparison rule for residual vectors. The word best has no meaning by itself. We could add absolute residuals, square and add them, focus on the largest magnitude, give some observations greater importance, treat large errors differently, or prefer smaller parameter values. Each rule encodes a different notion of closeness and defines a different mathematical problem. This lesson deliberately does not choose among them. Its purpose is to establish why a criterion is necessary. The next lesson will select and study one particularly important rule, least squares. Elect the complete progression. Exact observations satisfy y equals phi w. Noise or unexplained variation gives y equals phi w plus epsilon. Usually no available phi w equals y exactly, so we seek phi w approximately equal to y. The residual y minus phi w records the remaining disagreement. This is the bridge from solving simultaneous equations to fitting a model. At school, we solve two simultaneous equations. Now, in modeling, I want to guide you through how the same structure becomes phi times w equals y, possibly with thousands of observations and hundreds of features. Let us build this step by step. The advanced questions are still recognizable. Does a solution exist? Is it unique? Notice what happens here. Does phi have full column rank? Are the parameters identifiable? If exact equality is impossible, how should closeness be measured? Scale and noise enlarge the problem, but they do not erase its elementary roots. Several distinctions prevent common mistakes. N counts observations, while rank counts independent information. An exact prediction vector can exist even when several parameter vectors produce it. Full rank tells us effects are distinguishable. It does not tell us observations are noise-free. Noiseless data can still be rank deficient. Noisy data can have a full rank design. More observations can stabilize evidence, but cannot make an unsuitable family represent a fundamentally different pattern. Model choice and parameter estimation remain separate decisions. Let us diagnose 4 cases. First, a 3-parameter model with only 2 observations is underdetermined. Rank can be at most 2. Second, a 3x3 matrix whose third column is twice the second has enough rows but rank 2, so coefficients are not unique. Third, the rows 1, 0, 0, 1, 1, 0, and 1, 0, 1 form a full rank exact system and recover weights 1, 2, 3. Fourth, the line design with inputs 0, 1, 2 has rank 2, so slope and intercept are distinguishable, yet the noisy outputs 1.1, 2.9, 5.2 are inconsistent with exact equality. Full rank does not guarantee an exact fit. Pause for the checks. W0 through W3 gives 4 parameters, so at least 4 independent scalar observations are needed in an exact system. 5 identical observations provide 1 independent equation, not 5. If column 3 equals 5 times column 2, their parameter effects cannot be separated. 10 observations and 2 parameters can't have an exact solution if every point lies on the same line. Different noisy point pairs create different lines because the complete system is inconsistent. Finally, if y equals 7 and y hat equals 6.5, the residual is positive 0.5, the model underpredicts. Direct the tempting shortcuts. 3 unknowns do not need just any 3 points. They need 3 independent constraints. More rows do not always increase rank. A square matrix is invertible only when full rank. Overdetermined does not mean unsolvable. Perfect data may agree exactly. Noise and poor model choice are not the same. Enough data do not guarantee unique coefficients when inputs remain dependent. And an exact fit to finite observations does not prove that the selected model is the true relationship beyond those observations. Let us collect the lesson. Each observation evaluates the chosen features and becomes one design matrix row. All predictions satisfy y hat equals phi times w. In an exact system, unique identification of p weights requires at least p observations and full column rank. Rank means the columns express independent parameter effects. With dependent columns, some weights remain inseparable, regardless of row count. Real observations introduce unexplained variation, and a limited model family may add systematic mismatch. Then y equals phi w plus epsilon, exact equations usually conflict, and the residual vector y minus phi w records the disagreement. We have moved from exact algebra to a well-posed question about approximation. We can now state the next problem precisely. When no parameter vector satisfies every observation, how should the residuals define the best approximation, and how can we calculate the corresponding weights? In Lesson 3, we will answer that question using least squares. We will see why squared residuals lead to a geometric projection, how the normal equations arise, and what rank means for that solution. For now, the important achievement is conceptual. Approximation becomes necessary because noisy or mismatched observations make exact simultaneous equations inconsistent, while rank determines whether the parameter effects are distinguishable at all.